Many times in engineering, you don't really need the entire equation of the elastic curve because it's not so important what the displacement is at every single point along a loaded beam. Most of the time, what we're going to care about is we want to know the maximums. I want to know what's the maximum moment at a certain point of the beam, what's the maximum deflection at a certain point of the beam, what's the maximum slope at a certain point of the beam. And when we're looking for just the maximums, we don't really require finding out what the equation is to calculate everything through the beam. Why? Well, the maximums where the interesting things are going to happen. If the beam is going to break, it's going to break at the maximum point. And so that's what we need to calculate out. Now, so we have this method called the superposition method. And the superposition method is basically just that. We've used superposition before in this class. But what we're going to do is we're going to take a very complex beam loading, and then we're just going to add up all the different parts to get what the superimposed, full out, everything done version is. So let's take a look at a beam with a very complex loading. And so I'm going to use a cantilevered beam, and I'm going to stick it into a wall here. And so at the wall, we're going to have a reaction force, and we'll have a moment. Now on that beam, in the middle of the beam, I'm going to add a moment. At the end of the beam, I'm going to add a load, and then I'm going to add a distributed load on the first half of the beam. Now, if I was going to draw the moment diagram of this, it would look like this. A little curve that, and then it would flatten out. And so that would be our moment diagram. That's pretty complex. And this would be kind of a pain to have to do with the equation elastic curve, solving it from calculus and whatnot. Especially since basically what we're going to want to know is, what's the moment at that point there? What's the deflection at that point there? What's the maximum shear stress in it? So what we can do is we can break this up and superimpose the different conditions on each other to get the same thing. So this is all going to be equal to what? Well, let's break it up. The first thing I do is I've got a distributed load right here on the front. I mean, it's still got the reaction and the moment here, but if I put that distributed load on, I'm taking away the moment and the force. So what do I have? Well, on this side, if I look at my moment diagram, that's just going to be a decaying curve, just like that. Okay, so what's the next thing? Well, the next thing is I take my beam, and I look at that moment in the middle of it. Well, what happens there? Well, the moment diagram for this is just a box loading right there. And the last thing is we look at the cantilevered beam with the force at the end of it. And what does a cantilever beam with a force at the end of it? Its moment diagram, it's just a little wedge triangle. But if I take that, add that force to there, add that moment to there, what I'm going to get is I'm going to get a combined loading that equals all this craziness. And the same thing happens with my moment diagrams. As you can kind of see, you can see the different parts in there. So let's so this one down here, this down here will make the red one. If I look at that, well, there's the red. There's that part in there. And then we'll make this one here our green. Well, there's our green part there. And actually, that's probably a bad choice if you're red-green colorblind, huh? Because you have no idea what's going on. So let's pick a different color. Let's make it, make this one purple, I guess. And so there's our purple there. And then there's our black. We'll just leave our black right there to show this little part. So I've taken these and I've just added them onto each other. I've put them together. And that's it. And where do I get the... So what do I do? Do I sit here and I calculate out the equation of the elastic curve of the cantilever beam and then just add these all together? Well, you could do that, but we have standard tables that are used quite a bit from moment diagrams that you'll find in the back of the book. Table D in the back of your book, Appendix D, I'm sorry, in the back of your book will have some. You can go and use the engineer reference manual under the mechanics and materials section. There will be a couple common diagrams for different loading conditions. And there's different, so you can play around with this too, because I actually like these because it's kind of like a puzzle almost, because you're putting things together. One of the things we can sit here and go, okay, well, here's a cantilever beam with a distributed load at the end here. Well, how do I go about solving that? Well, I can find them like, oh, well, I can just assume I can take one beam here. I can find a table for the distribution being over the entire beam. Well, then I can add to that. Well, there's nothing going on here at the end, but I can calculate out right at the end of this, what's the slope? Well, if I know what the slope is, the rest of this is just a beam that's going to be at that slope, and I can use a little bit of trigonometry and go, okay, well, if I need to know what the deflection here at this last point is, if I know the slope, which would be the angle here, if I know the length, well, I can figure out what the drop off at the end is. So this is all what superposition is. It's, like I said, it's just kind of putting pieces of a puzzle together. We've got a couple examples we can show you how that works. And like I said, this one could be a little bit, instead of just hard grinding equations, it's piecing things together a little bit more of a puzzle.